All right, then for the last talk for this very special session, I introduce Bart Rosenzweig from the Ohio State University, and he's going to speak about maximally dissipative and self-adjoint extension of K-invariant operators.
All right, thank you. Yes, as Christoph said, it's the Ohio State University. Don't be confused. I think on the website it says Ohio State. It is indeed the Ohio State. Um, okay, yes, so the name of my talk is Maximally Dissipative and Self-Adjoint Extensions of K-invariant Operators. This is based on joint work with our two esteemed session chairs, Christoph and Jonathan. It's been accepted now, but you can find it on the archive. Um, okay, so uh, basically. Okay, so I have some introductory slides here, which I'll sort of speed through. I know I'm talking to all the experts here, but basically this is about uh, self-adjoint extensions of symmetric operators. So we all know what it means for an operator on a Hilbert space to be symmetric, right? Though my friends in physics will say that this just means it's self-adjoint, but of course this does not mean that it's self-adjoint. This means that the adjoint is an extension of T, right? And in practice, when one writes down, for instance, a differential operator, a second order differential operator that comes up in physics on the domain, the naive domain, it's a symmetric operator, but we want it to be a self-adjoint operator, which amounts to, right, defining the domain in the appropriate way. Um, so for all these reasons that we're familiar with, it's an important problem in quantum mechanics to understand, given a symmetric operator, how to write down self-adjoint extensions if they exist, and if they do exist, understand how many there are. Right. So this is a classical thing. The first major results on this are due to von Neumann, where he parametrized famously all the uh, self-adjoint extensions of a closed symmetric operator by the set of unitary operators between these so-called deficiency spaces, which are these like complex eigenspaces of the adjoint of T, right? So this is a bit abstract, but it does tell us when these extensions exist, right? Um, so after von Neumann, there's a lot of authors. Important names are Krein, Vishik, Bierman, and Grubb, and many others uh, studied, well, okay, let's say I'm given a closed symmetric operator, which is also non-negative. Can I understand self-adjoint extensions, which are themselves non-negative, which preserve this property? And this is sort of the theme of the talk. We want to understand self-adjoint extensions that preserve a certain property of the symmetric operator. Um, right, and so this is also a rich theory. Uh, that there's this nice structure uh, among the non-negative self-adjoint extensions of T. Namely, there's this partial ordering amongst all the non-negative self-adjoint extensions. There's this somehow biggest one, the hard extension in physics called the Friedrichs extension, and there's this soft extension called the Krein-von Neumann extension. And we tend to think of the Friedrichs extension. If this is a differential operator, we tend to think of this as the extension that imposes Dirichlet boundary conditions, and Krein von Neumann as Neumann boundary conditions. But that's of course not always true, as we'll see. Where the partial ordering is this one that comes from quadratic forms. Um, okay, and these extremal operators have this explicit characterization in terms of limits, which I'm just flashing here because we use it in an important way in our proofs. Um, this is all in a lot of references. And these, much like in von Neumann's theory, when he parametrized all these self-adjoint extensions of T in terms of this auxiliary operator, which in that case, these were unitaries between those deficiency spaces. Here, there's this Grubb, Bierman, Krein, Grubb, Vishik theory. It has all these names attached to it, which parametrizes all the non-negative self-adjoint extensions of, of a strictly positive closed symmetric operator T. Now, in terms of self-adjoint operators whose domain, the closure of the domain is contained in the kernel of T star. Uh, and the parameterization is given explicitly like this. Basically, this operator B somehow encodes the boundary behavior. Um, but anyway, uh, so more recently, there's a lot of works that where people try to understand self-adjoint extensions that preserve other properties enjoyed by the symmetric operator you start with, in particular symmetries. What do I mean by that? Here are some examples. So there's this paper by Makarov and Sekhanovsky. There's a lot of papers that do this, but here's just a couple examples that sort of inspired what we did. There's this paper by Makarov and Sekhanovsky where they study what they call mu-scale invariant operators. So if I have an operator T where there exists some unitary operator U such that if I conjugate T by U, I get back a scalar multiple of T, some positive scalar mu. And what they proved in this paper, among other things, is that the Friedrichs and Krein von Neumann extensions always of a symmetric operator which have this symmetry preserve this symmetry. Okay. And here's another paper by three by Ibort, and the other names are Yedo and Paris Pardo in Poincaré, where they studied the mu equals 1 case of this. So if my symmetric operator commutes with a unitary. And what they showed is that a self-adjoint extension, T sub V, where V is the corresponding unitary that comes from the von Neumann parameterization of self-adjoint extensions, that this self-adjoint extension commutes with this U, so preserves this invariance, if and only if the corresponding unitary does. Okay, so this gives a nice parameterization of the self-adjoint extensions which preserve the symmetry in terms of this, classical parameterization of the extensions. Okay, so this is this was sort of the jumping off point for us. Is so we basically defined another symmetry which like generalizes both of these, and we studied what self-adjoint extensions preserve those symmetry, but instead of relying on this von Neumann characterization of the extensions, we used that other Biermann-Krein Wishik parameterization, which is useful in applications when you're dealing with non-negative operators, which I'll talk about towards the end. Okay, so let me give the setup now for our work. So for now, forever let K be a bounded operator with bounded inverse, and T is a densely defined closable operator on a Hilbert space. So we say T is K invariant if K star Tk is equal to T, right? So this, right, in particular, if I define, like K is allowed to be unitary, in which case I have the case considered by Ebort and them. I can also define K to be like some multiple of like square root mu times U or something like that, and then with an appropriate power of mu in front, and then move that to the right-hand side here to recover the mu scale invariance, right? So this sort of generalizes what they were looking at in those papers. Okay, so what can I say if I know that an operator is K invariant? Here are some just things that one can calculate. The adjoint is also K invariant, as is the closure, right? Being the adjoint of the adjoint. And moreover, and this is like really important because this is sort of how we prove all the abstract results in the paper, basically, that a restriction of the adjoint of T, meaning if T is symmetric, right, a self-adjoint extension of T is going to be itself K invariant if and only if we have this equality, that if I take the domain of T hat, this restriction of T star, and I act on it with K, that set, this is the same as the domain of T hat. Okay, and this is a calculation which we do in the paper. And we use this to prove the first theorem. So let T be a non-negative symmetric K invariant operator. Right, so for our T, there's some K for which this is true. Then both the Friedrichs and Krein von Neumann extensions are K invariant. So this sort of generalizes the Makarov-Tsekhanovsky result. And so where does the proof come from? I'm not going to run through the whole proof, right? But basically, we just verify this equality here using those characterizations of the domains from a couple slides ago involving limits, right? And you can sort of insert Ks and K stars and move them around the inner products in there. Okay. So this is nice. Okay, so it's all a bit abstract for now. Let me give a sort of concrete example. So now let's define this very nice operator. So this is minus 2 derivatives on the half line. And if we define it on this domain with, basically like clamped at 0, H2 functions that are like clamped at 0, this is a non-negative symmetric operator. And it's well known that I can sort of parameterize all non-negative self-adjoint extensions by a coupled boundary condition at the endpoint 0, of this form, right? F prime of 0 is equal to mu f of 0, right? Mu is equal to 0. That is a Neumann boundary condition, right? F prime is 0. And we just take mu equals infinity to mean Dirichlet. So somehow, formally enforcing f of 0 is itself 0. Okay. So it turns out that this operator is K invariant. What is K for this? And this is basically, for all our examples, the prototypical K that we think about. We just think about a similarity transform, basically. So we scale the half-line by some positive parameter lambda. Okay, and then we divide by 1 over square root of lambda just to make like chain rule work out so that this operator T is indeed K invariant. Okay, I wrote down the adjoint here. So T is provably K invariant, and therefore, by the abstract theorem, so are the Friedrichs and Krein von Neumann extensions. I should say that here Friedrichs extension does coincide with Dirichlet, and the Krein von Neumann does coincide with Neumann. One of the cases where von Neumann and Neumann are the same. Okay. But if lambda is not equal to 1, we don't even have to use our abstract theory to understand which of these self-adjoint extensions are K-invariant. We could just compute, we could just try to verify that domain equality. And basically, if you work it out, you're actually forced to have either mu is 0 or infinity. So we can also just like see from just an elementary calculation that only Dirichlet and Neumann are the K-invariant self-adjoint extensions. This is sort of a trivial example, but what it says is one of the sort of interesting punchlines of our result, which is that, like, let's say I didn't know that that the Dirichlet and Neumann boundary conditions corresponded to the Friedrichs and Krein von Neumann extensions. This sort of tells me, right? Because I know that those are the only K-invariant extensions, but I also know that Friedrichs and Krein are always K-invariant. So one has to be Dirichlet and one has to be Neumann. Here it's not so interesting, but in other examples we'll see that just by exploiting the symmetry, you can sort of pin down what the Krein von Neumann extension is explicitly in terms of boundary conditions, which is not always possible in general. Okay. So moving on here with the more of our results. So we have a similar result, which has a sort of technical-ish statement and proof, but just to say, right, because it's important for how this relates to previous work, we have a condition on when self-adjoint extensions of strictly positive closed symmetric K-invariant operators are themselves K-invariant, much like in that Ebort paper, but instead of involving the unitary that comes from von Neumann's parametrization of the extensions, it's in terms of this operator B, which comes from the Biermann-Krein-Wischig theory. And it's very similar, okay? We have the P here is the orthogonal projection onto the closure of the domain of B. So it's just a little, it looks like their condition, but it's a little bit more technical. And in fact, if B, excuse me, if K happens to actually just be a unitary operator, which is the case they considered in that paper, then this does indeed reduce to their condition that the auxiliary operator B commutes with unitary. Okay. And also, I mean, I'm like contractually obligated to talk about maximally dissipative extensions because it's those are the first two words of the title. But basically, all the Biermann-Krein-Wischig theory also goes through for maximally dissipative extensions of symmetric operators, where now it's the auxiliary operator, the auxiliary operator B is now a maximally dissipative operator rather than a self-adjoint operator. But all this is still true. Okay, and we have so under some nice conditions, we can actually prove something like what we had in that other example, this sort of nice either or type of thing. In particular, if the kernel of the adjoint is of T is one-dimensional, then we show that either one of two things happens. Basically, you can calculate that the kernel of T star is spanned by an eigenvector of this operator encoding the symmetry K. And basically, if the corresponding eigenvalue, if the modulus is not equal to 1, then it turns out that all extensions of T are K invariant. Uh, and if it is equal to 1, then it turns out that it's only Friedrichs and Krein von Neumann, right? And basically right there, operator B basically becomes a scalar and you just calculate. Okay. So we sort of use this in some of the examples. I think I'm coming to examples now. Okay. So now let me just give a bunch of the examples that we gave in the paper uh, to give, to illustrate the theory. So the examples are all Sturm-Liouville operators. So let me just introduce our notation, which is standard, right? So a Sturm-Liouville operator, this is an operator um, given by a self-adjoint realization of some differential expression, second order differential expression, which looks like this, right? Um, Here's the technical conditions on these things so that, this will all make sense. And I give more in a bit, right? If P is 1 and R is 1 in particular, this is a one-dimensional Schrodinger operator on an interval, which may be infinite. Um, right, and as is well known, one can define this so-called maximal operator and the pre-minimal operators associated with this differential expression, right? Um, right, the maximal operator being like I require just whatever I need so that everything makes sense, that TF that F, for an L2 function F, if I act on it with tau, I get something in L2 and all the derivatives are defined, right? So F and PF are both AC loc, absolutely continuous on every compact subinterval of AB. And the pre-minimal operator, I assume even more. I assume that F is compactly supported. Okay, so what's the type of symmetry, capital K, we're considering, similarity transform? So basically, it's similar to that half-line example I gave earlier, that we like just transform the interval. So we precompose F with some diffeomorphism of the interval phi, and we also allow for a multiplicative factor out front. We have to assume a few things for this, right? So capital A and P times capital A are an AC. Um, we also assume that phi is so as I said, it's a C2 map of the interval to itself that like preserves the endpoints. We need the derivative doesn't vanish, and we need some other boundedness conditions. And importantly, we'll assume this condition on the weight function R, right? Notice R is like the weight function in the domains where we define this thing on. Um, this is an equation that actually shows up in dynamical systems called the Schroeder functional equation. I'll say more about that in a second. Okay, under all those assumptions, the pre-minimal, the minimal being the closure of the pre-minimal, and the maximal operators associated with tau are all K invariant. This is a calculation. If one imposes the following sufficient conditions on the coefficient functions, which are really complicated, right? But notice um, so as I said, that functional equation satisfied by R of x equals C R of phi inverse of x is this Schroeder functional equation. Basically, it's an R is like an eigenvalue of the composition operator associated with phi. Um, so P, if you stare at this for a while, P and P inverse, at least if A is constant, satisfy another similar equation that also comes from dynamical systems called the Julia functional equation. Basically, it's instead of a constant C out front, right? So A is just a constant here. Um, if instead of just a constant out front of this P of phi inverse, I also have the derivative of out here, right? So this is called Julia's functional equation. Sort of interesting that we end up getting these, right, well-studied canonical equations sort of popping out at us here. If A is not constant, it's whatever this is, right? And I'll say that if P and R are both 1, so if I'm dealing with a Schrodinger operator, the requirement for K invariance is still quite complicated. In particular, here it is, uh, right? So this actually restricts um, right, if A is a constant, then phi prime has to be phi has to be a linear function. So I'm very restricted. Um, if A is not constant, then the potential just has to satisfy some very complicated equation here. Okay, but we'll see some examples of this in just a moment. Okay, so one of our last important theorems is, so again, right, so we have this abstract result that parameterizes all the k-invariant self-adjoint extensions of operators in terms of those auxiliary operator B coming from Bierman-Krein-Vishik theory. Well, for this concrete case, we just did the regular setting, so all the there were assumptions of these coefficient functions being L1 log, just make them L1 now. Right, the self-adjoint extensions of the minimal operator are all parameterized in terms of boundary conditions, right? And so what we do is um, we have a theorem which tells us exactly what the condition on the boundary condition is to preserve k invariance, right? So for instance, um, um, there's either separate, so-called separators or coupled boundary conditions, right? Here's what it means to have a separated boundary conditions, right? And, an interpolation between Dirichlet and Neumann, basically. And so our theorem is the following, that, right, the Dirichlet extension is always k invariant, and we can actually, under some conditions on it just falls out of the calculation. It seems to care about the derivative of phi, this scaling of the interval, or transformation of the interval, I should say, and the is quasi-derivative of the coefficient out front, capital A. We can exactly specify what parameter in this separated boundary condition corresponds to a k-invariant extension, right? Sometimes it's pi over 2, right? Which is like a Neumann type condition at that endpoint. And under some conditions here, and under other conditions, it's some wacky thing. And under another condition, it's all of the angles, right? And then again, this falls out of the calculation, but it's very sort of interesting that seems to have this like either or. Either it's Dirichlet plus another one, which if it turns out that's the only one from our abstract theorem, that has to be the Krein-von Neumann extension, or it's either all or a whole zoo or infinitely many, some infinite family of them. Right here, I have the condition on this boundary condition at A, right? But it's the same at B, basically. And okay, just to flash all these horrible formulas, and there's also coupled extensions, right? And we have a corresponding theorem for those as well. A parameterization of the coupled boundary conditions that preserve this k invariance. Again, it's a calculation. Okay. Right. So as I said, as an application of these results, for specific choices of the parameters, frequently what you can do is you can pin down what boundary condition corresponds to the Krein-von Neumann extension, right? And it's not, possible in general for strictly positive operators. We can actually just construct what the Krein-von Neumann extension is, and this is given in this paper here, which I think you can see going to a glimpse of the future there and the references this paper. Krein-von Neumann extension revisited. Um, anyway, so it's sort of curious that you don't even have to solve the equation, right? Here, if you just know it satisfies some symmetry under some conditions on the symmetry, we can actually tell you what the boundary condition is that corresponds to Krein-von Neumann, right? And so what we do at the end of the paper is basically just construct a bunch of examples of this. And how can we do this? Well, since these sufficient conditions for the coefficient functions are these well-studied equations of Schroeder and Julia, we can just construct a whole zoo of examples of k-invariant Sturm-Liouville operators, and we can talk about which self-adjoint extensions are k-invariant. And here's just a couple of them. In fact, once you have one, there's all these ways of producing a family of other ones. These are sort of fascinating equations. Anyway, here's one example, right? So here, R and Q are 1, and I have this mu x squared for P in the middle here. If I take this similarity transformation of the interval 0 to 1, if you go back to the theorem and calculate what phi prime at 1 is, then since this is not equal to 1, we know that Dirichlet and Neumann are the only k-invariant boundary conditions. So this tells me that Neumann is the Krein extension. And we can also actually use our abstract theorem about the kernel of T star and the eigenvalue of k since this thing, the modulus is not equal to 1, I also have this. Okay, and lastly, here's just an example of a Schrodinger operator that satisfies this sort of symmetry. And again, this is sort of a curious operator, right? It sort of behaves like 1 over x squared at the origin, right? Sort of like Bezel, but it goes to a constant, right? As x goes to infinity. I think I have that right. So it's not like Bezel in that regard. Anyway, so here's this complicated similarity transformation, which this thing satisfies. It's a calculation using these known solutions, these functional equations. This thing is one thing that's curious is that this thing is reminiscent of it's not the same as this Eckhart model, which shows up in quantum field theory. And this model is very symmetric. In fact, it's super symmetric. But that's a totally different type of symmetry. So this similarity might just be superficial, but it is curious. And if anyone knows any physical applications of this or um, manifestations of this operator, that would be interesting to hear. Anyway, under some choices of the parameter, again, you could pin down which boundary condition corresponds to Krein von Neumann, and you could do the same thing. You can compute the eigenvalue of this symmetry operator K to also verify that we only have 2 K-invariant extensions in that case. And I think I am just on time here. So thank you. There's references, and I'll take any questions.
Thank you so much. Okay. Do we have any questions?
Can I have a question, please?
Yes, please.
Right. So the first question